Imagine a world not too far from our own, where the very laws of physics seem to bend, where what we understand about star formation and planetary orbits is irrevocably shattered. What if I told you that scientists have discovered such a place? A planet so utterly impossible it challenges everything we thought we knew? This isn't science fiction. It's a real-life cosmic enigma, a celestial body orbiting a star that by all accounts should be dead. But the biggest question isn't just how it got there, but what dark secret its existence truly hides. To unravel this profound astronomical paradox, we must journey to a place utterly alien to our solar system, yet surprisingly ancient. Our story begins in a distant, crowded neighborhood of stars known as Messier 4, or M4 for short. This isn't just any star cluster. M4 is a globular cluster, a dense, spherical collection of hundreds of thousands, sometimes millions of stars, all bound tightly by gravity. It's one of the oldest structures in our galaxy, a relic from the early universe, approximately 12.7 billion years old. To put that in perspective, our sun is a mere 4.6 billion years old. Imagine the untold eons that have passed within M4, the cosmic dramas that have played out. It's within this ancient, densely packed stellar metropolis that our impossible planet resides, a gas giant with the rather unassuming designation of PSR B1620-26b. But its unremarkable name belies a story of cosmic defiance. Normally, planets like Jupiter are thought to form in the relatively calm, dust-filled disks orbiting young single stars. The conditions in a globular cluster like M4 are anything but calm. The incessant gravitational perturbations from countless nearby stars make planet formation incredibly difficult, if not outright impossible, according to conventional models. Yet PSR B1620-26b exists. Adding to its bizarre nature, this planet doesn't orbit a normal single star. Instead, it's locked in a gravitational dance with a binary system composed of a pulsar and a white dwarf. A pulsar is the rapidly spinning, super-dense remnant of a massive star that exploded as a supernova, emitting beams of radiation like a cosmic lighthouse. A white dwarf is the cooling, compact core of a less massive star that has exhausted its nuclear fuel. Both are stellar corpses, celestial husks from a bygone era. For a planet to form around such a chaotic, violent, and ancient system, within an even more turbulent stellar cluster, is akin to finding an ice cube in a supernova. It simply shouldn't be there. This realization sent ripples of shock and excitement through the astronomical community, forcing scientists to confront the limitations of their understanding and hinting at a much more complex and perhaps terrifying truth about planetary formation in the universe. The initial detection of PSR B1620-26b wasn't a sudden, dramatic reveal, but rather a painstaking process spanning years of meticulous observation. The first hint came in 1987, when astronomers at the Arecibo Observatory detected unusual variations in the timing of the pulsar's pulses. Pulsars are incredibly precise cosmic clocks, and any deviation in their rhythm can indicate the gravitational tug of an unseen companion. Initially, these subtle wobbles were attributed to the presence of a white dwarf, which was later confirmed. However, even with the white dwarf accounted for, there remained residual, unexplained variations. It was as if something else, something even smaller and more elusive, was subtly messing with the pulsar's perfectly timed signals. For years, scientists continued to monitor the system, collecting more data, refining their models, and slowly, painstakingly, piecing together the puzzle. The idea of a planet orbiting such a system, especially within M4, was almost heretical at the time. The prevailing wisdom suggested that planetary formation simply couldn't occur under such extreme conditions. The sheer age of the system, at approximately 12.7 billion years, meant that if this was indeed a planet, it would be a true elder, possibly the oldest known planet in the universe. This earned it the affectionate, if slightly ominous, nickname Methuselah, after the longest-lived biblical figure. The implications were staggering. Not only was a planet discovered in an impossible location, but it was also a planet from an era where scientists thought planets like it simply didn't exist. This wasn't just a challenge to localized theories. It was a fundamental reevaluation of the timeline and conditions for life's potential existence across the cosmos. It implied a universe far more capable of producing diverse and unexpected planetary systems than we ever dared to imagine. It was a cosmic slap in the face to our carefully constructed models, forcing us to ask, if this planet could form, what else is out there that we're completely missing? But how could such an impossible world come into being? The prevailing theory of planetary formation involves a protoplanetary disk of gas and dust gradually coalescing around a young, stable star. In M4, the stellar density is so high that gravitational interactions between stars would quickly rip apart any nascent disk before planets could even begin to form. Furthermore, the violent supernova explosion that created the pulsar would have sterilized the immediate vicinity, ejecting or vaporizing any existing planetary material. So, what happened? The most widely accepted, yet still extraordinary explanation is not formation, but capture. Imagine a cosmic billiards game played out over billions of years. The theory posits that PSR B1620-26b did not form around its current host stars. Instead, it likely formed around a different, perhaps more ordinary star elsewhere in the cluster. But M4 is a dense, violent place. As stars constantly whiz by each other, their gravitational fields tug and pull, altering orbits and sometimes even ejecting objects. In this scenario, Methuselah was gravitationally ripped away from its original parent star during a close encounter with the future binary system. This was no gentle adoption. Such an event would have been an incredibly chaotic and energetic dance of gravitational forces, ultimately resulting in the planet being ensnared by the pulsar white dwarf duo. This gravitational capture theory is not without its own challenges. For a planet the size of Jupiter to be captured and then settle into a stable, long-term orbit around two stellar remnants is an incredibly improbable event, requiring a precise alignment of cosmic coincidences. Yet it remains the most plausible explanation for a planet defying so many established rules. But there's another, more unsettling possibility lurking in the shadows. What if our understanding of planet formation is fundamentally flawed? What if, in regions of extreme star density, or around stars we once thought incapable of hosting planets, entirely different mechanisms are at play? What if the universe has a hidden capacity for creativity that we are only just beginning to glimpse? The search for answers to Methuselah's origins continues, a testament to humanity's relentless curiosity. Its existence forces us to broaden our cosmological horizons, to consider possibilities once relegated to science fiction. It reminds us that the universe is a place of infinite surprises, capable of producing wonders that defy our most sophisticated models and deepest understandings. For now, PSR B1620-26b remains a silent sentinel. Billions of years old, an impossible world orbiting dead stars in an ancient cluster, a constant reminder that the cosmos holds secrets far stranger and more profound than we can currently comprehend. And perhaps that's the most thrilling mystery of all, the enduring potential for the unexpected, waiting to be discovered just beyond the edge of our current knowledge. If you want more cosmic enigmas, be sure to check out our next video where we explore the Great Attractor, a mysterious gravitational anomaly pulling our entire galaxy towards it.